Space exploration has always been one of the greatest frontiers of human achievement, and robots have played a critical role in advancing this mission. Space robots are machines specifically designed to operate beyond Earth's atmosphere, where conditions are too harsh, distant, or dangerous for humans. These robots can range from rovers and landers that explore planetary surfaces, to robotic arms that assist with satellite repairs and International Space Station (ISS) operations, to autonomous drones that scout alien terrains. They are considered the eyes, ears, and even hands of humanity in outer space, performing responsibilities that range from scientific exploration to maintenance, resource extraction, and planetary defense. Without them, much of the progress made in space science over the last 5 decades would have been impossible. The primary applications of space robots are vast and diverse, each tailored to specific challenges posed by space environments. Planetary rovers such as NASA's Spirit, Opportunity, Curiosity, and Perseverance are designed to travel across the surface of Mars, collecting geological samples, analyzing soil and rock composition, and searching for evidence of water or potential signs of life. Similarly, landers like the European Space Agency's Philae, which landed on a comet, demonstrate the potential of robotic technology to reach and study environments far beyond human reach. Beyond exploration, robotic arms such as Canadarm and its successor Canadarm2, mounted on the Space Shuttle and ISS respectively, are used to capture satellites, assist in station assembly, and conduct maintenance operations. These robots carry out responsibilities that would be extremely risky, time-consuming, or impossible for astronauts, thereby extending the reach of human ingenuity. Space robots also serve a vital role in constructing and maintaining orbital infrastructure. The International Space Station, one of humanity's most ambitious engineering projects, relies heavily on robotic systems for repairs, cargo handling, and the deployment of scientific instruments. Autonomous space drones are being developed to refuel satellites, repair aging hardware, and even remove dangerous space debris orbiting Earth. These applications demonstrate that robots are not just exploratory tools, but also caretakers of the growing space economy, ensuring that assets remain functional and sustainable. With the emergence of commercial space industries, robotic spacecraft and drones are being envisioned for asteroid mining, lunar construction, and long-duration exploration missions that humans cannot yet undertake. One of the most crucial responsibilities of space robots is scientific research. They are equipped with specialized instruments that allow them to study planetary atmospheres, surface geology, radiation levels, and potential resources. For example, Perseverance rover on Mars carries instruments capable of detecting organic molecules, measuring weather conditions, and preparing samples for future return missions. These scientific investigations lay the groundwork for potential human colonization by determining whether environments are habitable, how dangerous conditions might be, and what resources can be used. In this way, robots act as both scouts and guardians of human expansion into the solar system. To function in such demanding environments, space robots require robust power systems. The two most common energy sources are solar power and radioisotope thermoelectric generators, RTGs. Solar panels are widely used on spacecraft and rovers operating relatively close to the Sun, such as Mars rovers and satellites orbiting Earth. They convert sunlight into electricity, which powers onboard systems and recharges batteries for operation during dark periods or at night. However, in environments where sunlight is weak or intermittent, such as deep space or the outer planets, RTGs are the preferred option. These devices convert the heat released by the decay of radioactive isotopes like plutonium-238 into electrical energy. This technology has powered missions like Voyager 1 and 2, which are still operational after more than 4 decades in interstellar space. In addition to these methods, emerging power solutions include advanced batteries, nuclear reactors for long-duration missions, and potentially even energy beaming from Earth or orbital stations. The way space robots work depends on a combination of autonomy and Earth-based control. Onboard systems include sensors, cameras, robotic arms, wheels or tracks for movement, and scientific instruments tailored to the mission. Robots operate through both pre-programmed commands and real-time adjustments. Since communication between Earth and distant robots can take anywhere from several seconds to hours due to the speed of light, autonomy is essential. For example, a Mars rover cannot be steered like a remote-controlled car in real time. Instead, it must make decisions such as avoiding obstacles, choosing safe routes, and handling unexpected challenges on its own. This requires advanced artificial intelligence, machine learning algorithms, and adaptive programming. Communication with Earth is one of the most vital aspects of space robotics. Robots typically use radio waves to transmit data back to Earth-based receivers. Depending on their location, they may rely on relay satellites, as in the case of Mars rovers that send signals to orbiters before the data is transmitted to Earth. Deep space missions depend on powerful transmitters and the Deep Space Network, DSN, an international array of large radio antennas capable of receiving weak signals from billions of kilometers away. Communication is not just about sending data but also about receiving instructions, which can include daily commands, new navigation routes, or adjustments to experiments. The delay in communication requires that robots be equipped with high levels of operational independence, so they can continue working effectively even when waiting for new instructions. Beyond exploration and research, space robots also play a role in ensuring human safety. For example, robotic scouts can explore hazardous environments such as high radiation zones, extreme temperature regions, or areas with unstable surfaces before astronauts arrive. This not only minimizes risks, but also increases the efficiency of human missions. In planetary defense, robots could potentially intercept and redirect asteroids that pose a threat to Earth. NASA's DART mission, which tested the deflection of an asteroid using a kinetic impactor, is an early example of how robotic spacecraft could protect our planet from catastrophic impacts. Another emerging application of space robots is in construction and resource utilization. As humanity plans missions to the Moon and Mars, robots will be tasked with constructing habitats, extracting resources like water ice, and producing fuel from local materials. These tasks would be logistically and physically overwhelming for astronauts but are well suited for robotic systems. Robots may build landing pads, solar farms, and protective shelters using 3D printing technologies combined with local materials. Space robots also raise questions of ethics and responsibility. As autonomous machines, they operate with a degree of independence, but the consequences of their actions can have long-term implications. For instance, a mistake in collecting samples or altering a planetary environment could compromise future research or even violate planetary protection guidelines. Therefore, engineers and mission planners must design robots that not only perform tasks effectively, but also follow strict protocols that minimize contamination and environmental disruption. The responsibility of space robots is therefore not limited to accomplishing tasks, but also ensuring that scientific integrity and ethical considerations are upheld. The physics of how space robots operate is fascinating and deeply tied to the unique conditions of space. For instance, on low-gravity planets like Mars or the Moon, mobility systems must account for different traction levels, slopes, and stability issues. Rovers use specially designed wheels with treads and suspension systems to handle rocky terrain. In orbit, robotic arms and spacecraft must contend with microgravity, requiring precise control to avoid unintended movements that could destabilize their position. The principles of momentum, inertia, and energy conservation are constantly at play in these machines, making their engineering a marvel of applied physics. Looking toward the future, the evolution of space robots is likely to be shaped by advancements in artificial intelligence, miniaturization, and collaborative robotics. AI will allow robots to learn from their environments and adapt more effectively to unforeseen challenges, making them true partners in exploration rather than mere tools. Swarm robotics, where multiple small robots work together in coordinated tasks, may become common in planetary exploration and construction. Miniaturization will make it possible to send fleets of small robots rather than a single large rover, increasing efficiency and resilience. These innovations could revolutionize not just space exploration, but also humanity's ability to establish permanent settlements beyond Earth. The collaboration between humans and robots in space is another crucial aspect of future missions. Robots will not replace astronauts but rather complement them. For instance, while robots can handle repetitive or dangerous tasks, humans can provide creativity, improvisation, and problem-solving abilities. This partnership will be particularly important in long-term missions to Mars or beyond, where the challenges will require both robotic precision and human adaptability. Furthermore, the commercial space industry is accelerating the development of new robotic systems. Companies like SpaceX, Blue Origin, and others are exploring ways to use robots for rocket recovery, spaceport operations, and extraterrestrial construction. The push for space mining in particular will likely depend heavily on robotic technologies capable of extracting, processing and transporting resources from asteroids and other celestial bodies. Despite their incredible potential, space robots face limitations and challenges. Power generation remains one of the biggest hurdles, especially for missions beyond Mars where solar energy is less effective. The harsh conditions of space, including extreme temperatures, radiation, and dust, can also degrade robotic systems over time. Communication delays limit real-time control, and the cost of launching and maintaining robotic missions remains high. Addressing these challenges will require ongoing innovation in robotics, materials science, and energy systems. The evolution of these technologies will be iterative, built on decades of experience and new breakthroughs in autonomy and power. The collaboration between robots and humans will define the next era of exploration, enabling missions that are safer, more sustainable, and far-reaching than ever before. Space robots will not replace human ingenuity, they will amplify it, acting as our reach and our guardians as we step farther into the cosmos. Thank you for watching.